Okay, part 3, number 22. The 3 vehicles shown below are all traveling at a speed of 15 meters per second. So each one of them has the same speed of 15 meters per second, 15 meters per second. But only the pickup has a changing velocity. Well, they all have the same speed, and we know velocity has 2 parts. It is speed, which in this case it's not changing, it's all the same, but it also includes direction. So if the pickup truck is changing velocity and it's the only one changing, then the only thing that can be affecting that velocity is a change in direction. So the question states the pickup truck has a changing velocity because the pickup truck can accelerate faster. Well, we don't know anything about the acceleration of any of those cars, and the acceleration has nothing to do with changing velocity. It's traveling in the opposite direction. They're all traveling in the same direction, and even if you didn't know that, traveling in the opposite direction of something does not mean you're changing velocity. It's traveling on a curve. A curve means that you're changing direction. Which is changing your velocity. And J needs to move large amounts of force, and that might be a true statement, but that's not why it's changing velocity. It's changing velocity because it is turning on a curve in the road. Okay, number 23. 2 trains are traveling down a track. Train A has more mass than train B. A has more mass than B. What will happen when the 2 trains attempt to stop with the same force? So more mass, same force at the train station. A, the train with the smaller mass will require less time to stop. If it has the same force applying to it, a smaller mass would have a bigger acceleration or a bigger deceleration or negative acceleration. So it would require less time to stop. So this one is looking pretty good right now. The train with the larger mass will require less time to stop than the train with the smaller mass. The larger mass is actually going to have less of an acceleration, so that means it's going to take more time to stop. The train with the smaller mass will take longer to stop. The smaller mass would have a bigger acceleration or a bigger negative acceleration in this case, so it would actually stop faster. And the train with the larger mass will have less inertia. Larger mass means it has more inertia, not less inertia. So that is not our answer. A is going to be our best answer. Okay, number 24. During a tug-of-war competition, neither team is able to gain an advantage, which the following explains the forces in this situation. If neither team is gaining an advantage, that means they must be balanced or no net force, which means they're not changing. So the forces are balanced if neither one is taking an advantage. Remember when we did our tug of war outside, when y'all were not moving, you were balanced. The forces are overcome by air friction. No, air friction would not have anything to do with this tug of war. The mass of the rope cancels the forces. No, the mass of the rope does not cancel the forces. And the forces are unbalanced. If they were unbalanced, then that means they would be changing motion. One team would be winning. So the best answer is F.
Hey, hold on.
Okay, number 25. Which of the following scenarios best describes Newton's laws of action-reaction? A bottle of soda sitting on the console of a vehicle appears to move left as the vehicle makes a sharp right turn. That is going to be the law of inertia. So that is not action-reaction. A rocket moves up as the engine pushes down. So the rocket's moving up, the engine's pushing down against the gases, and the gases are pushing up. That is the action-reaction. So that would be definitely the third law. I like this one so far. A train traveling 88 kilometers per hour takes approximately 1 mile to come to a complete stop. This is going to be its speed. This is how long it takes it to stop, so that's acceleration. So that is going to be Newton's second law, or force equals mass times acceleration. And D, an ice skater sharpens the blades of their skates to lessen the effects of friction. This doesn't have anything to do with any of Newton's laws, so the best answer is going to be B. Okay, number 26. Which of the following best illustrates an application of Newton's first law, also called the law of inertia? So that is for every action. That is an object at rest stays at rest, and an object in motion stays in motion unless acted on by an outside force. So F would be a passenger not wearing a seatbelt is ejected from an automobile in a severe crash. So you're in a car and you don't have a seatbelt on, the car stops, you are going to continue flying forward. Dinner plates remain on the table when a slick tablecloth is pulled out from underneath them. They remain on the table, so they are stopped. As it pulls out, then they will remain where they are. Their inertia keeps them there. An ice hockey puck continues sliding across the relatively friction ice until a player comes in contact with the wall or sticks it. All of these are examples. So the puck is moving, it's going to continue moving until it hits a wall. All of these are examples of Newton's first law. Yes, they are all great examples of Newton's first law of motion, or law of inertia. Okay, number 27. A roller coaster containing 4 cars is accelerating at 15 meters per second. So there is the acceleration before it comes to an abrupt stop at the end of the ride. The mass of one car, so one car has a mass of 200 kilograms. How much force was exerted on the roller coaster to bring it to a stop? Well, we know that force is equal to mass times acceleration. We know that the mass is going to be 200 times 4, because there are 4 cars, so the mass would be 800, and we multiply that times the acceleration, which is 15 meters per second squared, giving us a force of 12,000 newtons, letter D. Number 28, a 62 kilogram wakeboarder is being pulled by a boat with a force of 124 newtons. That's the force. This is the mass. What is the acceleration of the wakeboarder? Well, again, we have to come back to our formula, our little triangle. We're looking for the acceleration. So the acceleration would be equal to the force divided by the mass. The force is 124 newtons divided by a mass of 62 kilograms. We plug that into our calculator, giving us 2 as our acceleration, h. Okay, 4 tractor trailers are entering a highway. Their masses and net forces are recorded below. There's the force, there's the mass. Which tractor would have the greatest acceleration when entering the highway? We could do this using our math, which is force equals mass times acceleration, looking for the acceleration. So it would be force divided by the mass. So we take these and we divide each of these by the mass. We could do the math on that and we can see which one has the biggest or the greatest acceleration, so that's the largest number. Or we could think logically, guys, which one has the smallest mass? The smallest mass is going to be number 4. We know that the smallest mass will have the, well, this one actually has a different acceleration, a different force, so we do need to do the math on that one. So the first one would be 7,000 divided by 3,800, giving us 7,000 divided by 3,800. Giving us a 1.8. Next one would be 7,600 divided by 4,000 is 1.9. The next one would be 7,000 divided by 4,500, which is about 1.5. And then the last one is 7,600 divided by 3,200. Giving us a 2.4, rounding up. So definitely the greatest acceleration is that last one that has the smallest mass, and it actually has the larger force. So letter A, tractor trailer 1, because the mass and force are less compared to the other tractors. We'll know it's not trailer 1 for sure. Trailer 2, it's not trailer 2, it's not trailer 3. Trailer 4, because the mass is less and the force is greater. D is our best answer. And finally, number 30, a group of 4 students is participating in a marble race. Each marble has a different mass and the same force is applied to each one. So the forces are all equal, they have different masses. Which one will have the least acceleration? So that's going to be the smallest acceleration. Which one will have the smallest acceleration? It's going to be the one that has the largest mass. If they all have the same force, the larger mass will have the least acceleration. D has the largest mass. So we could do the math on this. We could divide each of these by the mass. But if we did that math, then D is going to have the smallest number right here. So without even doing the math, because we know that the largest mass will have the smallest acceleration, then D is going to be our correct answer, or J will be our correct answer. All right, so that's it for your physics unit test corrections on the dump. So in order to receive credit for your dumping, what you need to do is make sure you copy everything that we write. If your dumping grade is below whatever it is, if it's a 60, 70, 50, it will go up to 100 as long as you copy everything that we've copied and turn this in. These will be due by next Wednesday, so you'll have a little bit of time to work on it over the weekend. This will be done completely on your own. We will not have class time for this, so you'll need to get it done on your own time and get them turned in by next Wednesday. On Friday this week, we will be doing some reteaching and retesting for those of you who were not successful, did not show mastery on the actual test. The recording for this is only for the dumping grade, which also counts as a test grade. Please let us know if you have any questions, and good luck.